Hello everyone, welcome back to our third lesson in this machine learning fundamentals series. Today we're going to be covering supervised learning. So what can you expect to learn from today's lesson? We're going to be of course covering what supervised learning is. We'll also distinguish between the two different types of supervised learning, namely regression versus classification. We'll talk about some classic algorithms used, such as linear regression, logistic regression, decision trees, and more. And we'll look at some key concepts and terminology, such as underfitting, overfitting, training versus testing data. Let's get right into it. So, first and foremost, what is supervised learning? In a nutshell, supervised learning is when you have a training data set for the model. So a training data set with features X and labels Y. And so the model learns by mapping X to Y. Pardon me. And so you can think of it like a student who is studying from a textbook, whereby the correct answers are already provided to them. So over time, you can imagine that the student, aka the model, is going to be able to figure out patterns as to how to arrive at those answers by looking at many different examples to understand, okay, I understand how to derive at the answer now, having seen a sufficient number of examples. And so it's called supervised learning because the presence of this labeled data acts essentially as a teacher guiding the model. The model gets feedback on whether its predictions are right or wrong during training. It has the ability to self-analyze and check to see how it's doing, essentially. Right, so as mentioned previously, we have two different types of supervised learning, regression versus classification. And so we use either a regression model or a classification model depending on the goal of what we're trying to achieve or the output of the data. So we'll start with classification, as I believe it's more simple and easy to understand. So with classification, a classification model, we'll use a classification model where the goal is to predict a discrete category or label. I'll give you an example. So we have an incoming email, for example, and we want our model to simply decide whether this incoming email should be labeled as spam or not. And so by looking at the patterns of the email, let's say for example it will look at the heading of the email, oh, a missing heading, or if there's links in the email, okay, maybe it'll look at these things and say, okay, if there's links in the email, if there's no previous contact with the person before, if the subheading uses certain keywords or there's a missing subheading, we're going to label this as spam, for example. And so different other examples of where we would use a classification model is if the goal is to predict if an applicant will default on a loan or not. Does this person approve for a loan? Yes or no? Or diagnosing a disease. Does this person have this particular disease? Yes or no? And so classification is all about classifying or categorizing this piece of data. And so it's much more binary. It's much more yes or no. The answers are much more limited. Okay? So contrast this with regression, where as opposed to the output being very binary, the output is much more flexible. It's more on a scale, more on a range. And so a good example would be predicting a house price. So let's say, for example, we have a very simple example. We want to know the price of a house that is based in central London and it has 3 bedrooms. Okay, so these are the metrics that we'll use. Of course, in a real life scenario, we'll have much more metrics that we look at, not just location and how many bedrooms the house has. It will look at things like material and does it have a garden and etc, so forth. Alright, but for simplicity's sake, we'll just take these two metrics, location and how many bedrooms that the house has. And so our model will look at the patterns, the previous data, and say, okay, houses within central London that are 3 bedrooms, they're usually priced at XYZ price. And so it will use that data to predict the house prices. And so as opposed to with a classification model, it's not so binary. The answer is not just yes or no, or just a few options. It's not classifying into a category, but the output is predicting it could be from a vast range or array of numbers. Alright. So other examples would be forecasting a stock price or estimating a person's weight from their height. So if a person is 6'1", we might estimate, okay, looking at previous data that we have for people that are 6'1", they tend to weigh 80 kg or whatever it may be. Alright, and so that's the difference between regression versus classification in a nutshell. And so we use different algorithms depending on whether our goal is regression, the data we're working on is going to, the outcome requires a regression model versus a classification model. And so some popular algorithms would be linear regression, which is where we use a straight line approximation of the relationships. Polynomial regression, where a straight line won't do, so we use a curved fit for non-linear data. Or we have things such known as random forest regressor, an ensemble method combining decision trees. Popular algorithms for classification include logistic regression. Despite its name, this is used for classification, and we'll get into all of these a little bit later. Decision trees, random forest trees, XGBoost, and support vector machines. So, to summarize the key difference, regression outputs usually a number, where classification outputs a class, label, or multiple labels, trying to categorize something. Alright. So the classic algorithms explained simply. Linear regression idea, it fits a straight line that best predicts the output from the input features. And its use case is predicting continuous outcomes like sales, prices, or scores. Logistic regression, instead of a line, it fits a logistic sigmoid function that outputs a probability for belonging to a certain class. Its use case is, as we discussed, for binary classification. Spam or not spam. Default, will this person default or not default? Decision trees. The idea is that the model splits the data up based on features. Is feature A greater than number 5? And then it will essentially branch off until it reaches a prediction. And so I'll give a much better scenario. So it will ask a series of yes or no questions, and depending on the answer, it will then branch off into another decision tree. So you can say, let's say we want to work out if this picture is a picture of a cat or if it's a picture of a dog. So you may ask the question, does it have ears? Yes. Okay. Does it weigh more than 10 kilograms? No. Okay. Does it have whiskers? Yes. And it will keep going down this decision tree, filtering out the similarities until so it can confidently predict and decide, okay, this is a picture of a cat. I hope that makes sense. It wasn't the best example, but that's essentially what a decision tree is. Ensemble methods, e.g. random forest. So the idea is to combine multiple decision trees where each tree votes or averages the outcome. And so the benefit of this is to reduce a term known as overfitting, and it's often more accurate than a single tree. So with a random forest decision tree method is when you take the output of the first decision tree and it filters into the next. So an analogy for this you can think of, say for example, you have a teacher marking a student's work, and let's say this teacher gives that student 60%. With a random forest tree, you'll take that answer and then give it essentially to another teacher who then double checks the work. And so it's essentially getting a more accurate answer where your work is double checked, let's say by 5 or 10 teachers as opposed to simply just one. Okay? The training and testing paradigm. So how the model essentially works, we have a training set, so this is the data that the model will see and learn from. Then we'll train the model, so we'll tune the model's internal parameters so that it predicts the labels accurately. Then we'll have like a testing or validation set, so this is a separate data slice which is not used during training so that we can test to see how well our model performs with data that it hasn't seen. And then we'll evaluate how well the model generalizes to the unseen data. So why does this matter? If you only check performance on the training set, you might fool yourself into thinking that the model is perfect when it has simply memorized the training data. And so this is where overfitting and underfitting comes in. So overfitting means when the model learns the training data too well, and so it's capturing noise or random fluctuations rather than true underlying patterns. And so the symptoms are it will have high accuracy on training data, but poor accuracy when it comes to actual test data or unseen data or real life scenarios. An example, a decision tree with 50 levels might perfectly fit training data but fail on new data. And so you can think of it essentially like a person going into an exam, right, who has memorized a certain set of exam questions, but when they go into the exam, because they've simply memorized only those questions and those particular answers, when a different question comes up that is off of the same type of concept, let's say it's a mathematical equation asking how many apples does John have, these types of questions, where because it's now using different names, it's now a different scenario, the person is completely thrown off. Or for example, someone that only memorizes flashcards but doesn't understand the underlying patterns or theory or how to arrive at a particular answer. They've only memorized that particular answer, so when they go into the exam they struggle. That's essentially what overfitting is. It's being too familiar, only memorizing very specific answers, and so when certain things have changed, they've not comprehended the underlying concepts of what is actually being taught. And so overfitting, that's essentially what overfitting is. It's being too specific with training data and not understanding the underlying patterns. I hope that makes sense. Underfitting is essentially the opposite. So the model hasn't learned enough. The model hasn't learned the underlying pattern well enough. And so the symptom is it will simply have poor performance on both training and test data. Alright, and so using the same example, this is when the student just hasn't done any sort of study, hasn't done enough study. And so when they go into the exam, they'll fail either way. And so what are some ways that we can mitigate overfitting and underfitting? We'll go into more detail into this, but simply we can simplify the model. So include fewer features. We can use what's known as regularization, L1 and L2 techniques. Again, we'll go into more detail. We'll also, for underfitting, we need to collect more data, or we can use more powerful models, add features and reduce regularization. Okay, so here's a conceptual walkthrough of what actually building a simple model will look like. What is a process of building a simple model? So first we want to gather data, then we'll split the data. It's usually done 80% for training and 20% for testing. We'll then choose a model. Let's say we'll do like a linear regression model, for example. We'll then train the model, so we use an algorithm to train the model on, and we'll then evaluate. We'll predict on the test set, compare predictions with the actual scores, and we'll use a metric known as, for example, MSE or R squared. Again, don't worry, we're going to walk through what all these things mean in just a moment's time. And the last step is to refine the model and to look for where the model has failed, what can be improved essentially. Now, so let's take an example where we have this goal. We want to predict exam scores. So of course this is going to become into a regression model as opposed to a classification model. So we want to predict a student's exam score. So this is dealing with numbers, right? So we're going to use a regression model. So we want to predict a student's exam score based on the hours that they have studied. Our supervised learning model will learn this relationship. Hours studied, this is the X, versus the exam score, Y. So our model's job is to learn the pattern that the more study time generally leads to higher scores. As you can see, if someone studies 3 hours, then on average their score will be 65, etc., etc. So we want the model to learn this general pattern. Okay, so how will we do this? First, we're going to split the data. So before we can train our model, we must divide our data strategically into training data and testing data. And here's an example. Okay, so 1 hour, okay, score 50. If the student studies 2 hours, on average they score 55, etc., 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 etc. Okay, so the training set teaches our model the patterns. The testing set is what we're going to be used to evaluate how well our model performs, to see if it's learned correctly. So this split prevents a model from simply memorizing data, which again is overfitting, which we covered previously, and it must generalize in order to succeed, which is what we want, right? So step 3, we need to choose a model. Linear equation. Exam score equals this formula times hours studied. Okay, so we'll use a straight line which will draw the best possible line through our data points, and the interpretation is the intercept. So this is the score when the study hours equals 0, and this symbol essentially represents the slope, so how much the score increases per study hour. So linear regression will give us a simple yet powerful way to model the relationship between study time and exam performance. And so the algorithm will find optimal values and minimize the prediction errors. Alright, so the next step will be to train the model. So the first step will be to feed in our training data. So the algorithm analyzes our hours and score and pairs. No, I'm not starting again. Right, so step 4. So first we would feed the training data. The algorithm analyzes our hour and score pairs from the training set. Find optimal parameters. So using ordinary least squares, OLS, it will minimize the total prediction error. Again, we'll get into this in more detail. So we'll identify the line with the smallest distance to all points, and no complex math is needed for understanding, so don't worry. Generate our equation. So our model produces a score, let's say 45 plus, there should be a brackets here, 5 times the number of hours. And so the intercept will be 45, expected score with 0 study hours, and the slope will be 5, so each study hour will add 5 points. Alright? And so now it's time for the prediction. So example, if a person does 8 hours of study, we take the intercept score, which would be 45. So if the person didn't do any study, then we'd expect them to score 45. But because they've done 8 hours of study, we'll do 5 times 8 plus 45, and we get 85. Okay, 5 times 8 is 40, plus 45 equals 85. So we expect, if this person does 8 hours of study, we expect 85, score of 85. Okay, and so step 5 will be to evaluate the model. So with our model trained, we now test its performance on unseen data to validate its predictive power. And so we're going to be using a method known as MSE in order to do this. Okay, and I'm going to show you on the next slide. So just bear in mind, this person has studied 9 hours. This is the actual score. This is what our model has predicted. And so we've got an error of being off 4 points. Okay, and again, when we're evaluating the model, this is the actual score that the student got, but this is what we predicted based off of our training data and our methodology, and so we're only off by 1 point. Okay, and so this is the MSE algorithm. So now that we've evaluated our model, let's understand our primary error metric known as MSE, mean squared error. So what is it measuring? It's the average of squared differences between predicted and actual values. It penalizes larger errors more heavily. And so let's have a look at the interpretation. So lower values indicate a better model performance. Our score of 8.5 shows reasonable accuracy. So what's actually going on here? So we have our score here of 4 and our score here of 1. So if you go back to the previous slide, we have our error here of 4 and our error here of 1. Looking at the difference between the predicted and the actual score. And so we put this into this formula, which is the mean squared error. And so we have 4 squared plus 1 squared divided by 2. This is the formula for mean squared error, which we use. And so this will essentially equate to 16. 4 squared, 4 times 4 is 16. 1 squared is 1. That's 17. 17 divided by 2 is 8.5. And so this is essentially just to give a value so that we can at a glance see how well our model is performing. And so a lower score, of course, represents a higher form of accuracy. So the lower, the better. If we have a score here of 3, it means that our model is very accurate and only is off by very, very few points. Okay. Y-square. Squaring prevents negative and positive errors from cancelling out and gives greater weight to outliers. Comparison. MSE 8.5 versus MAE 2.5 shows our errors are consistent with major outliers. Alright, so don't worry too much if you don't fully understand, but it's simply to know that this number, we want it to be as low as possible, and the lower the better. Okay, we also have something known as an R-squared score, which measures the model's quality as well. Beyond error metrics, we need to know how much variance our model explains in the data. And so again, a useless model will score 0, a perfect model will score 1. 0, you can think of this as a percent, and 1 also being represent 100%. And so if our model scores 0.95, this essentially means that our model has a 95% accuracy score, you know. And so with an R squared of 0.95, our simple linear model captures nearly all the relationship between study time and exam performance. So that means we have an excellent model. And so the final step is simply to refine the model. So after evaluation, we can improve our model's performance by addressing 2 common issues. Identify the problems. So analyze error patterns to determine if our model is overfitting or underfitting the data. We can apply what's known as regularization to penalize complexity when the model performs well on training data but poorly on test data. And we also address our underfitting. So add polynomial, what's known as polynomial features, hours squared, to capture how we capture curved relationships when a linear model is too simplistic. Lastly, implement the new equation. Transform our model from the old formula essentially to the new. Essentially applying the changes and testing the data again. Right, and so finally, key takeaways from today's lesson. So supervised learning relies on labeled data. You can think of the model as in having a teacher. Regression versus classification. So we looked at regression predicting continuous values or numbers, whereas classification predicts categories or distinct classes. Training and testing data, splitting the data into training and testing ensures that we're not simply just memorizing the data and fooling the model, thinking that the model works well, and then it doesn't work well when we provide it with unseen data. And lastly, we looked at what overfitting versus underfitting is. So it's finding the right balance of complexity, ensuring that the model is not simply memorizing data, but that the model also has enough information to go off of, and making sure that the model is not too complex and removing additional categories that perhaps don't need to be there. So we refine the model as we go.